So the glucose molecules are just going to go down.
I did have one, but I didn't
There. All the sodium that's going to explicitly back into the water. Ion. Very good. C+.
Bless you. Wait, no, this bottom part is wrong. So this is the inside of the cell. So that's all we need to write.
Anything else?
And so then, like on the other half, like on the bottom, is it supposed to be high? Draw another sodium channel.
Where?
And it's down.
What does it say for sodium?
There's lower sodium in the limit.
Like initially. But this high, that's where the, and then it becomes high.
You're not allowed to. It's just because the pump has to make it higher.
Right. Oh, yeah. You're joking. That is true. High enable. That is true.
So going out that chain.
The gut. So what happens to the rate of production of ATP in these cells to whom the blood flow has been reduced?
It will decrease.
That's right. Now why?
Because most of them will be going to the muscle to power it.
Most of what goes to the muscle?
ATP.
Well, is there ATP traveling in the bloodstream? All right. So most of what? Aaron?
Blood. So oxygen, basically, going to the muscles.
Okay. Oxygen is one thing that's going to be reduced to those cells.
Oh my god.
Sir? And glucose. So these two things that your cells need to make ATP by aerobic respiration, which is the major way your cells are making ATP, will be reduced. So that's going to decrease your production of ATP because you have fewer reactants in that equation. How does this change in ATP production, which we now know is a decrease, affect the rate of glucose transport by secondary active transport from your gut into your body? Well, I have Ravneet who just talked. That's all.
Well, we said it would slow down because the rate of ATP production will decrease in the gut, but the cell could realize this and then start making more, just absorbing more.
So how could so the cell is getting glucose by secondary active transport, right?
Yes.
So what could it do to absorb more glucose to make up for that deficit?
It could.
Okay. Can the cell make up for it? Wait, let's see. Keelan, what do you think?
Well, we said that it would slow down the rate of glucose transport because you need, we already said in the first question that you have less ATP production. You need ATP to pump out the sodium, to pump in the glucose. So if you have less ATP, you can't pump in the glucose any faster no matter how much you want it.
Right.
Agree, disagree?
No.
Joe?
Is it possible for more glucose? Oh my God, that freaks me out.
Be proud.
Is it possible for more glucose to sneak in with than like, is it like 1-to-1 always? Because that would increase the glucose.
Define sneaking.
Well, riding on the back of, I don't know.
So
them.
I'm thinking about them. So what method of transport was that they used?
Well, it was secondary active transport.
Okay, secondary active transport. So is it if there were two Katies, or if Katie and Mo were out there, could Mo have also snuck in with Sandeep?
Yeah, is that possible? That's what I don't know.
Can Sandeep only take Katie, or could he take Katie and Mo, both glucose molecules, in with himself? What do you think? Should I pick a volunteer?
I don't know if it's a 1-to-1 ratio, but I remember reading that the sodium glucose transport, wasn't it a symport protein? So doesn't that mean it will only it can only have like two things going at once? Do you know what I mean?
I do know what you mean. I do. So let's think of it this way. Let's say Sandeep was an enzyme that made Katie from a glucose into a fructose. Could he convert 2 kDs at once?
No.
Why not? He can't handle it. Why not? What does an enzyme have or do that needs that? Steve?
Active site.
One active site. And what does that mean? What is an active site, an enzyme? What is that? It's the place where what?
The enzyme and substrate get catalyzed.
The place where the enzyme and substrate bind, we could say, meet and do that, all right? So you might not know much about transporters yet, but you can think of them like enzymes. Same thing. So when Sandeep's over here binding to Katie, and the way we did it wasn't perhaps so precise in our little animation, right? But he has one binding site. That protein has one binding site, and actually the sodium and glucose don't even touch each other. But the transporter has one site for sodium, one site for glucose, and transports across. So sadly, there can be no sneaking. But thank you for bringing that up, because people often believe in sneaking. All right? I won't tell you about Santa either. Right? That's our next one. Okay. So the rate of glucose transport decreases as described by Keelan and others. In addition to nutrients like glucose, water is also absorbed across the intestinal wall. When the rate of glucose transport decreases, how will that change the rate of water absorption? I have Brian and Team 8 to explain. What happens to the rate of water absorption, right?
I think the water absorption is going to decrease as well because it's going to follow glucose across the membrane. So if glucose absorption decreases, then water should as well.
Agree, disagree with Brian? Oh, Steve, you're at the other end of the room, my friend. But all right, get a chance to run. And then we go.
I don't think it would necessarily follow the glucose, but the water from the cell would actually diffuse out through simple diffusion because the equations glucose outside the cell is more than inside the cell.
So the the water will move where?
Outside the cell.
Okay, and in general, where does water move?
Towards a higher concentration, osmosis, to the higher concentrated area.
Higher concentration of?
Of solute.
Good.
Yes.
Of anything, and the only solute that's changing here is glucose.
Yeah. So my problem is you basically disrupt the sodium-potassium pump because you don't have ATP, right? So you wouldn't be able to pump sodium out of the cell, which means you'll have a higher concentration of sodium inside the cell. So that's pointing osmosis this way. But then the glucose would be pointing osmosis the other way because you can't get glucose into the cell.
So you have less sodium coming in, but less sodium being pumped out, less glucose coming in. If we're going to involve sodium, we have to involve sodium's secret friend, Adam.
So potassium's going the other way, so I guess, even though there's different numbers of ions, it's like 3 to 2, but potassium would be going the other way though, so I guess the effect would cancel each other out with respect to sodium and potassium.
Okay, so sodium and potassium will almost cancel each other out. Plus, where's our sodium? Who was sodium? Sandeep was sodium? No, Sandeep was sodium. Okay, so Katie, be sodium now. Good, come over here and be sodium. Okay, so I'm pumping you out. Get out. And then you're diffusing back in through your transporter. So if we stop one of those movements of Katie, we stop both of them, right? So that should cancel each other out by itself. Although I think the point about the pump is good in general. That's going to mostly cancel itself out as well.